Hello, today is Tuesday, December 8th, 2020. It is 1:05 CST in the afternoon here in southern Wisconsin. It is a brisk 32 degrees, which, Brad, what is that in Celsius? It's a flat zero.
Oh yeah, you're right.
Here's one case where I do like the US system over the outside of the US system because we get to say it's 32 degrees instead of zero. But I got back from my lunchtime walk. It's windy and cold out there. But today we're going to be talking about mechanical property testing and the trouble with dog bones and how the parts that come out of the Filamet process are different from casting and machining. So first, let's talk about the difference between Filamet full metal parts and the parts that come from casting and machining.
Okay. Yeah, people immediately, when they see our materials, they talk about 3D metal, everyone wants to relate it to casting, milling, forging, lathe, that kind of a thing. And it's a little bit of a struggle. And our strategy that we've sort of chosen is to educate people to think about it a little bit differently. The problem with the dog bones is its shape. One of the methods of densifying our parts as they sinter, as they need to get smaller. When you print them, there's plastic between the metal particles, but as you heat it to remove it, it obviously leaves a void. Something needs to happen with that space. So what happens is surface tension will draw the whole object down, it'll shrink. And while shrinking, it can distort. And this is a struggle not only with several types of 3D printing, but it applies in metal injection molding and things like that. So these aren't new problems. These actually go back decades. The key problem with the dog bone is its shape. And I wasn't thinking, or I have one to hold up, but they're, maybe 8 inches long with wider tabs on each end, and then it's narrower in the middle so that it'll force it to break in the spot that you expect when they do the tensile test. But what happens during sintering is the shoulders on the dog bone prevent it from shrinking and densifying properly. So you wind up with a sort of a artificially weak example.
I do have one. Grab that.
Okay. There's a number of solutions. We were settling on more of a tensile bar than a dog bone, just a simpler shape to get people to where they want to be. Right. And during the sintering process, that would actually get, probably a 1/2 inch shorter. And if you prevent it from getting shorter, it creates weak points, and that's where the breaks will always form. And
the ends are kind of shrinking together, and that refractory is holding those shoulders in place, so that middle shaft becomes the natural weak point.
Right. And this is the go-to shape for everyone that tests our materials, and they all have essentially the same result. So our technique or our strategy for managing it is to simply let it shrink or create a slightly different shaped part where it doesn't matter. So we've settled on more of a tensile bar than a dog bone. I think I might have one.
Right. So the result is that when we do strength or tensile testing with that dog bone shape, it's not representative of the strength that's possible with this process. So we're getting data that really isn't representative of the kind of parts properties that you can get from FFF metal.
Yeah, and the key problem here is trying to make that relationship back to existing technologies. The way going forward, and the way I expect the industry to evolve is designing for additive manufacturing. If you consider these properties in your design, they're pretty, they're not difficult to overcome. So much of this goes back to education. And one of the strategies, or a growing developed concept is generative design. And the generative designs tend to work really well in the filament process. They tolerate the shrinking and they just tend to work well.
So you're talking about one option, and that is just to change the part shape.
Right.
So we can go from wider tabs, narrower shaft. If we just made this the same width all the way across, that's one solution.
Yeah, that'd be fine.
Another option is to change the test itself. Is there a different piece of equipment that would give us a good piece of data?
Right.
And then a third option is to change the end result. So I know that you're working on, and in concert with our sintering partner, Sapphire 3D, are working on liquid phase sintering. Tell us about that.
Right. So in liquid phase sintering, you use a secondary metal that is liquidous below the sintering temperature of the base metal that you're starting with. So if you start with 316L, for example, it won't melt until about 1300 C. But you can put bronze in contact with it, and it'll soak it up like a sponge. It'll fill all the voids, and we're seeing rates of shrinkage that are 1%. And I actually think we can get it down to 0%.
So rather than ending up with a part with some porosity that can be affected by longer sintering types, further densification, things like that, with this liquid phase sintering process, you're ending up with a fully solid part.
Yes, and they're very strong and remarkably strong. And again, this isn't a new technology. This is something we've appropriated. It's been around for decades, but it's very common in some places and not so much in others. Powder metallurgy in general is a rapidly developing technology right now. Even outside of additive manufacturing and 3D printing, just dealing with the powdered metals is an explosive point of growth on the technology side of things.
So it really feels like this liquid phase sintering development is the next phase in what we're able to do and what we're able to offer. And the status of that right now is that you have been able to perform this liquid phase sintering and get a really, really strong part out of it a couple of times. So now we're at the point where we're going to bring that to a repeatable process that we can tell others about.
That's correct. And we've done pieces, and this is actually something we can put hard numbers on. I'll go back and we'll do something with a dog bone or a tensile bar. We just haven't quite gotten to that point. But we are in the development cycle. We're at a phase where I'm able to do it, just not consistently. Working with Sapphire, we expect to make this into a repeatable process that we can share with our users. And the end product is a very significant development in this whole concept. You wind up with a solid part with no shrinkage, which is incredibly interesting.
At that point, are we comparing those parts to cast parts, to machined parts?
Yes, we can start to compare them. They're still going to be different. And this is something people are just going to have to start to understand, that additive manufacturing is not milling, machining, or casting. It's its own thing, and it kind of deserves its own category and its own way of being thought about.
That's a great point. So in some cases, it can be a replacement, right, but it's really a brand technology that is creating its own niche and its own place in the world of manufacturing.
Right, and people are realizing that you can make shapes that you could never make before. I mean, everything that we've created since the Industrial Revolution has been a cylinder on a mill, or a square, or a cylinder on a lathe, or a square on a mill. 5-axis machining changed all that, and or 5-axis CNC changed that and made much more complex shapes accessible. But those techniques tend to be prohibitively expensive and take a lot of skill.
So 3D printing comes along, and in more specifically FFF metal by the Virtual Foundry, and now a whole new world of shapes is available at a much lower skill level.
Correct. And we think that it changes the way that things are made in so much that people will begin to understand that they can make things they could never make before, or they can solve problems they couldn't solve before, or they can solve problems in a way that they never knew that wasn't previously possible.
So Autodesk just released an article about a case study that they did with the Virtual Foundries Copper, Filamet, and STS Technical Services, which is near Milwaukee, Wisconsin. And in there, they were excited to be able to present their Fusion 360 software alongside our product and STS engineering background to provide a low-cost solution to an expensive problem. So that article was just released, and they also presented about that in FormNext 2020 about a month ago. So information about that is available on our website and through our mailing list. Now, we are hosting a Sintering webinar this Thursday, December 10th. If you'd like to sign up for that, reach out to us at info@thevirtualfoundry.com.
Right, and we'll cover all these topics in some depth, and it'll be very interesting. The project that we did a case study with Autodesk, but part of the longer term project with them is adding support for the Virtual Foundry materials directly into Fusion 360. So they're developing CAM software, and they call it Fusion FFF. So it'll be their contribution to FFF Metal, and the Virtual Foundry will be right there with it.
Great. I'm excited about that.
Me too.
Is there anything else you want to talk about where dog bones are concerned, tensile testing, part shape, liquid phase sintering?
Right. People just think outside the box, think big, think different, and we're going to revolutionize a lot of different things here.
I have one more important question for you before we wrap up the podcast. Do you know why a chicken coop has only 2 doors?
No.
Because if it had 4 doors, it would be a chicken sedan.
Nice.
All right. Thanks for your time.
Right.
Wraps up Volume 1, Episode 2 of the Virtual Foundry Podcast. We'll see you next time.